So how do we actually conduct signals? We have to deal with electricity, and we will eventually have to deal with chemicals. For now, let's focus on the electricity. Your nervous system is literally conducting electrical signals because we set up what we call membrane potentials. And membrane, this is the plasma membrane in your cell. So this is in a nerve cell, keep in mind. And this membrane potential is measuring the difference between the inside and the outside of the cell. The nerve cell, right? You can do this for any cell, actually. You can look at the difference in charge between the inside and the outside. But we're most interested in it for nerve cells because that change is what is actually going to help us conduct a signal. So at rest, so when your nerve is just waiting around for something to happen, we have what we call a resting potential. And this is literally, you can measure this with microelectrodes on either side of the cell, either side of the plasma membrane. And we are literally looking at the difference between the potassium and the sodium concentrations inside and outside of the cell. So inside a cell at rest, potassium is high and sodium is low. Outside, we look at potassium being low and sodium being high. Now, I know this might confuse some of you because how can we look at differences if these are all positive, right? All of these ions are positive, so how do we look at differences? We're going to look at differences in concentration, okay? So you notice that there is a large amount of sodium, huge amounts compared to potassium in your system. So out here we've got 12 sodiums, and we've got 2 potassiums. So total, we get 14 positive charges, right? Inside, we've got 2 sodium and 8 potassium, a total of 10 positive charges, right? So what we want to look at outside versus inside the cell is what is that difference, okay? We want to look at what is that difference in ion concentration because as you see all of these plasma membrane proteins that are set up here, including a sodium-potassium pump, remember, that costs us ATP. We've got channels, we've got facilitated diffusion going on, we've got active transport going on. At rest, you are maintaining this balance, unequal as it is, of positives outside and positives inside, but there's a difference, right? 14 minus 10 is 4. There is a difference. 14 does not equal 10. So there is a difference, and if you would put a microelectrode on one side and one on the other side, you would actually be able to measure a difference in charge between the inside and outside of this membrane. So a stimulus is anything that is going to cause us to change that resting state potential. And what we look for is a change in permeability. And that change in permeability will alter the sodium and the potassium concentrations inside and outside of that cell. So the change in permeability is going to allow ions to move. And if you allow the sodium and potassium ions to move, what we see in the long run is something known as an action potential. So we're going to go from that rest, that basic state, to some maximum level and then come back to rest. The basic action potential, if you literally measured the voltage, looks like this. So you have rest, You have some maximum level, and you have a return to rest. This is an action potential. What I want to show you now is how we actually make it happen. And it's all about changes in ion concentration. So, if we're hanging out at rest, we look at the resting potential being about minus 70 millivolts. So this is if you measured the difference between the inside and the outside of that neuron, inside and outside of that plasma membrane, this is what you would see. Remember, we had more positives outside and less positives inside. So what that means is we're actually subtracting inside minus outside to get our millivolt difference between the inside and outside. So in this case, we would have 2 minus 4 gives us a minus 2. That was when we were talking about ions. If you actually measure the difference in millivolts, it sits at about minus 70 millivolts for this resting state. And at rest, things are closed off. Nothing's happening. What we're waiting for is a nervous signal to come in and open sodium channels. So step 2 is open sodium channels. And this is only if a signal is detected. And we're going to open some sodium channels. This is important. Only some of them. And you see, we get this little blip. If you open sodium channels and sodium comes in, now maybe we have 3 positives outside and 2 positives inside. There's still a difference, but there's less of a difference, right? So we still have negative here in our membrane potential. What we want to see is if we reach what we call a threshold. If we reach the threshold, which is about minus 55 millivolts, if we reach that, if we let enough positives in that membrane voltage difference is now about minus 55 instead of minus 70, then we open more sodium channels. If you open more sodium channels, more sodium rushes into the cell. As it rushes into the cell, the inside becomes more positive. So now maybe we have 1 positive outside and 5 positives inside. So now we've got 5 minus 1, so that gives us a positive 4. And you see that we go positive on our millivolt scale. And we peak at about plus 37 millivolts. 37, 40, something in that range. And that's where we're going to peak. We have opened all the sodium channels we can. That's all we have to do so far. All of these sodium channels opened. To come back, we have to close the sodium channels and open potassium channels. We're going to open the potassium channels, and when we do, potassium is going to rush out of the cell. We're blocking sodium from coming in. So as we block sodium and we let potassium leave, we're going to build up again a larger concentration of pluses outside than pluses inside. And if we measure the difference in the millivolts now, we come back down to about where we started. If we had our out and our in, and we had blocked sodium from coming in across our membrane, we blocked sodium, but we were letting potassium out, right? But we want to stop it from coming out, but this is unfortunately is a slow closing gate. So if you've ever tried to move through one of the automatic doors and it's closing slowly and you sneak through before it closes completely, you are sneaky potassium. You just snuck through there, and because you snuck through there, you made more positives outside than we were supposed to, and we get a bigger difference in that membrane potential than we were supposed to. And you see here we drop down to nearly minus 90 millivolts. Well, we don't want to be at minus 90. We want to be at minus 70. So how do we come back? We're going to need those sodium-potassium pumps we've talked about before. To return to a resting state, we're going to need sodium and potassium to be pumped where they're supposed to be. So sodium gets pumped out, potassium gets pumped in, and we eventually get back to that minus 70 millivolts that we wanted at rest. And you see that we return to rest. This all happens in milliseconds. It's a very, very fast process. With action potentials, they only go in one way. So we had our dendrites, our cell body, our axon. We only ever send signal in one direction. Dendrite to cell body to axon. We never go the other way. We also have what we call all or none events. Either you're going to send a signal or you're not. This is not a little bit of a signal. You either get a signal or you don't. We'll look later at what it means when something hurts, when you smell something more strongly, when light is brighter. That's different. These are still all or none events. What we're going to look at is the number of events you get. Feel some things as kind of a minor pain versus a major pain. Maybe you consider biology to be a minor pain, but physics to be a major pain. We still look at the same cells, the same neurons conducting this information. What we have to look at is how many are conducting that information.